Hello, welcome back. This is Calculus by Dr. Oz. Today I'm going to go over three examples of functions like sine x, 1 over 1 minus x, and e to the x at different c points like power 4, 2, and 1. And what we're going to do today is just we're going to find a Taylor expansion or Taylor series centered at c for those functions. But before I hit the road, let me just give you a few definitions that we're going to use along the way, even though I'm going to go over those within the video, just to give you more heads up before you start hitting the road. All right, here we go. So the form of a convergent power series. First of all, once a function is provided to us, its power series is written in the form of an times x minus c to the power of n for all x in an open interval containing c. So we have the interval of convergency for that. But this an here, the n term, has a very specific form. It's in fact the nth derivative evaluated at c divided by n factorial. And as you see that, n starts from 0 going all the way to infinity. If you expand that infinite sum, you can actually write everything explicitly. So the very first term here is just f of c, and the next term is f prime of c times x minus c, and the second derivative c divided by 2 factorial x minus c squared, and you can just keep going as you increase the order of the expansion. But this is an infinite series, so this goes all the way up to infinity. And the second thing I want to share with you today is the definition of Taylor and Maclaurin power series. Let's say like you have the f, you have the derivatives of f at all orders at the given center, let's say x equals c. Then the series, which I just showed you in the previous slide, is written explicitly of that form, that the nth derivative evaluated at c divided by n factorial x minus c to the power of n. So this is an infinite series. So this is called the Taylor series for f at the center c. And if c is specifically equal to 0, then the series is called the Maclaurin series. So essentially, the power series that we obtain is called the Taylor series or Maclaurin series at the given center. Okay, so this was the second thing I want to show you. All right, the third thing I wanted to show you is the convergence of Taylor series. So here, we define R sub n of x as the way we did in the previous sections. So it's written in terms of the n plus first derivative of f evaluated at c. To say that the Taylor series of a function is convergent, we have to prove that the Rn, which is the tail of the infinite series when you cut off at n, right? Because the very immediate term is starting with the n plus first derivative. So Rn is represented by that. So that has to approach 0 for all x for you to say like Taylor series is convergent, and it converges to the function that you start with. What I mean by that is like if you have sine x and if you have the Taylor series of that, for you to show that the series is convergent and in fact convergent to sine x, you have to prove that the Rn, the tail or error, if you want to call it in another context, so that must approach 0 as n goes to infinity for all x. So these were like the three things that I'm going to use in this video, maybe in the videos of other exercises. So let's get started. All right, we're going to use the definition of Taylor series to find a Taylor series centered at c for the given functions. Here we calculate. First find the derivatives of f. So f prime as cosine x, f double prime equals negative sine x, f triple prime is minus cosine x, and the fourth derivative of that is sine x. And if I really want to have the fifth derivative, that's going to be cosine x. So if you keep going like this, the next term here, the next derivative is going to be negative sine x again. So you see this looping behavior for every 4 derivatives. Okay, so that's our first observation. So it's periodic in that regard. So all I want to do now is to evaluate these the function itself and the derivatives at pi over 4. So I'm going to evaluate at f at pi over 4, f prime at pi over 4, f double prime at pi over 4, and triple prime, and finally the fourth derivatives, and then all the rest is going to repeat themselves. Okay, so f pi over 4 is at this moment you may have your TI-84 with you, and you can take a look at sine pi over 4, but just keep in mind that we always want to keep the exact values for the trig values if possible, and pi over 4 is a known angle. So I would, in fact, use the unit circle instead to grab the values of all sine, cosine functions at pi over 4. Okay, so in that regard, this is radical 2 over 2. Cosine is also at pi over 4, radical 2 over 2, and you have minus sine, that should be negative radical 2 over 2, and negative cosine, so the triple, the third derivative evaluated at pi over 4 is negative root 2 over 2, and finally this is root 2 over 2. So as you see that the values of the derivatives evaluated at pi over 4, they're all of the form of radical 2 over 2, but the sign alternates, okay, in some sense, okay. All right. So going back to this description here, so I have all the values of f evaluated at the center point, right? In our case, it's pi over 4. We can go ahead and represent the sum, the Taylor expansion of sine x as first. Let's show it. Let's just represent it with the infinite sum. So the nth derivative at pi over 4, x minus pi over 4, well, to the power of n, all divided by n factorial. Okay, so let's just write that down explicitly now for starting from n equals 0. So n equals 0 is f of c. So sine pi over 4, that's radical 2 over 2, right? So I'm going to go ahead and write radical 2 over 2. So the next one is f prime at pi over 4, so plus radical 2 over 2 x minus radical 2 over 2 x minus pi over 4. Let's go back to second derivative evaluated at pi over 4. That's negative radical 2 over 2. So I can continue with this as negative radical 2 over 2 x minus pi over 4 squared over 2 factorial. Okay, let me continue from here. And then the third derivative, I think we got that as negative radical 2 over 2. So the third derivative evaluated at pi over 4. So we can go back and then plug that back in. Okay, so x minus pi over 4 cubed divided by 3 factorial. Okay, and finally, I think the fourth derivative at pi over 4 was like radical 2 over 2. I can go ahead and then type that in. Okay, and this goes obviously on and on and on. Okay, so if you just write them explicitly, it goes on. Let's sort of like write this in a very clean form. So, well, we can factor the radical 2 over 2. So now I have 1 plus x minus pi over 4 minus x minus pi over 4 squared over 2 factorial minus x minus pi over 4 x minus pi over 4 cubed over 3 factorial, and then plus x minus pi over 4 to the fourth divided by 4 factorial, and on and on and on again, right? On and on and on, because every single term starting from the very first term comes with radical 2 over 2, so we factored that out. So now the question is like, can you write this in terms of, can you generalize this and write it in the summation form, like with the summation n starts from 0 going all the way to infinity, okay? So let's check if we can do that, and since the sign alternates time to time, so we have to figure out how we can sort of like blend that in the power series, okay? So radical 2 over 2, so I'm going to write this as like sum starting from 0 going all the way to infinity. Well, first of all, this term comes along all the way as like the power n plus 1, because the very first term is supposed to be a constant term, right? The very first term is a constant, okay? So when n equals 0, well, n equals 0, we will have a constant. So I should probably reserve that constant right here. So 1 plus, okay, 1 plus. The next term is x minus pi over 4. That is in fact what that comes with n equals 0. Okay, so I put the constant out, and the very first term starts with x minus pi over 4 to the power of 1, and that should come along with n plus 1 factorial. That's 1 factorial for n equals 0. Okay, and then I'm going to write this first and discuss about it. And n minus 1 over 2. So let's try to write this for n equals 0 just to see if what we write here is correct. Okay, for n equals 0, the exponent here, minus 1 to the power of n minus 1 is going to be 0. That's 0th power of negative 1, that's 1. And when n equals 0, x minus pi over 4 to the power of 1 divided by 1 factorial, that's exactly what the first term is, okay, x minus pi over 4 only. Okay, so the next term in the sum, should come with a minus sign. Okay, should come with a minus sign. Okay, let's check. All right, so that's n equals, that should be n equals 1 case, right? So if n equals 1, let's see, 1, 0, that's minus. That is x minus pi over 4 squared over 2 factorial. Right, I think that should be plus 1. Otherwise, it doesn't work, right? So instead of n minus 1, we should have n plus 1. So let's try again. N equals 0. The power is 0 for negative 1, and negative 1 to the 0 is 1. The first term is x minus pi over 4. The second term, when n equals 1, 1 times 2 divided by 2, there you go. So we get 1 for the power of negative 1 in the case of n equals 1. So we have a negative sign coming along here, negative sign, x minus pi over 4 squared over 2 factorial. And when n equals 2, it's 2 times, 3 times over 2, that's an odd power, right? So that becomes minus x minus pi over 4 cubed over 3 factorial, and let's try n equals 3. 3 times 4 divided by 2, that's to the power of 6, which makes it a positive term. Here we go. Because I was looking for the pattern like plus, minus, minus, plus type pattern. That's exactly what it is. So this power term, n plus 1 over 2, takes care of having like plus, so here plus, right? Minus, minus, plus, and then minus, minus, and on and on and on. Okay? I think that takes care of part A. For part B, please move on to the next video. Bye.